There we go. Oh my goodness. That was obnoxious. So I was ready to start like a minute ago. And then I accidentally hit a button and it changed where my slide was. And it took me like 3 tries to get it to go to slide 40 or whatever slide we're on. But that's okay because we like listening to the ambience that is Secret of Evermore. Welcome back to Chem 161. Let's see here. Quiz number 3 is due today. So do that. Make sure that you get that done. It will close tomorrow. It's stretch, sorry. I'm still coughing a little bit, so I may have to mute from time to time, so I apologize for that. Feeling better, though, from Tuesday where I was feeling like, oh no, am I catching something? Now it's just like clearing it out, so. On Tuesday, we talked about electronegativity, we talked about naming stuff. We didn't get through acids, so we're going to learn how to name acids today. We're going to get through that, and then we're going to draw Lewis structures for literally everything. Today's lecture is probably the most important if you are a biology major, going on to organic chemistry. Because we're going to draw the Lewis structure of things. We're going to talk about all the different exceptions that you could do. We're going to do multiple bonds. And then we'll finish that off in Chapter 5 with a more thorough understanding of how bonding works and orbital overlap. So we got to get there first, so let's do this. There is a lab this week that is due, lab number 4, and I just realized that there's a lot of that involved. I think what I'm going to do is for lab number 4, I'm going to put a separate video up where I talked about how to do the lab last quarter. In the last quarter, I was able to put in the course catalog like lab periods, so I could spend an hour talking about how to do lab number 4. I don't really have an hour to talk about lab number 4 right now. So I will go looking for that video. Let me write a note to myself to remind me to do that. Where is my, let's see here, to do. I have a little document that just says to do. Let's see here. Chem 161. Link a video for lab number 4. There you go. It's not due this week. Sorry, it's assigned this week. It'll be due next week. But yeah, I'll get that up there tonight so that that is available. I've talked about it like 4 times, so I'm sure that I have 4 different videos on it. But it is very, very heavily Excel-based. Because if you don't use Excel to calculate the formula commands and then just copy and paste those formulas, it will literally take you hours and hours and hours to do the lab. If you know how to use Excel, or every time I say Excel, replace with Google Sheets, you can do the lab in 10 minutes because you just draw the formula once, or write the formula, and then just drag it through a bunch of cells and then just copy and paste. So the point of this lab is not necessarily quantum mechanics, but learning proper Excel techniques. It's just that this is the point in the quarter where we actually hit quantum mechanics. So we have just finished it, but that lab is going to look at the hydrogen spectrum in some detail. All right, let's name some acids here. Acids are always indicated by having... Oops, sorry, I hit the wrong button there. They are always indicated by having an H plus in the front of them. The first element in an acid must be hydrogen. That's how you know it's an acid. Now, sometimes H's will pop off and sometimes H's won't. In the case that there is both acidic hydrogens and not acidic hydrogens, we write things like this. So, for example, for acetic acid or vinegar, this H is the acidic H. But these H's that are written elsewhere are not acidic. So only some number of hydrogen ions will pop off of an acid, and those are written in the front of it. Now, the reason that H becomes acidic is due to the nature of the bond between that H and the other ion. When a hydrogen is attached to a very electronegative ion, or not ion, I'm sorry, atom, the electron density shifts towards the electronegative atom and away from H. If you do that enough, the H plus will pop off, and the electrons that it were shared in the bond then belong to the electronegative atom. So, for instance, in HCl here, here's what my Lewis structure for HCl would look like. We haven't gotten to Lewis structures, but this will make sense a little bit later. If I just take these electrons away, then what I end up with is this and that. So if I just take the electrons from hydrogen and say, I want these, then H plus will pop off and we create the effect or phenomenon of acid. Now you can make an acid out of most polyatomic ions, and you will add enough H pluses to neutralize the charge on the ion. So here I have phosphate, which is 3 H pluses, because the charge on phosphate itself is -3. So I need 3 of these to balance it out. There are 3 different naming rules for acids, and so the trick is going to be to look at the ending of the polyatomic ion that you are looking at to name an acid after. So the first rule, your textbook lists as binary acids. Oops, I didn't mean to tap the screen there. But I am going to list it as acids with ions ending in "ide." So any ion that ends in "ide" follows the rules for what we have here as binary acid. So that would include fluoride, chloride, sulfide, etc. And here are the rules for naming that. In these acids, the state matters. If you have a gas for your acid, we name it like we would name it as a covalent compound. Hydrogen plus whatever. But if the acid's in the aqueous state, we use this other rule, which is much more common. We use the word hydro, and then we put the stem of the ion in there, so that'd be like sulfur would be sulfuric and would become sulf. Chloride would become chlor. Iodide would become iodo or iode. Things like that. And then you add ic acid. So for instance, if I had HCl here, I would write hydro blank ic acid, and I'd put whatever stem for Cl goes in here. So that would be chlor. And this is all one word, hydrochloric acid. Now, because cyanide ends in "ide," it also follows these rules. So HCN we would call hydrocyanic acid. You just chop off the "ide," put the stem in there. Sorry, there was screaming outside, and I realized it was just a child playing, so I was concerned there. Hopefully my mic didn't pick that up, because I was like, what the hell? Alright, so here are some acids. You'll notice that I have labeled their states. The states are important for naming. So what I want you to do is name each of these acids based on the information shown. I got HBr and HF as gases, HBr and HF as aqueous. Type in some names. We'll go over the answers in about 1 or 2 minutes. All right, let's go over the answers here. So we've got HBr and HF as gases, so we're going to call these hydrogen, and then whatever they are. So this would be bromide. And hydrogen fluoride. Yeah, fluorine is tricky to spell. Make sure you don't spell it flower-eyed, like the stuff that you cook with. HBr as an aqueous would be hydrobromic acid, and then HF as aqueous would be hydrofluoric acid. All right, there you go. So binary acids, very straightforward. Oxyacids are the majority of acids that we're going to name in this class. They're basically polyatomic ions that have oxygen in them. And so what we're going to do is we're going to use these naming schemes if you end in either 8 or if you end in 8. So if your ion ends in 8, remove the 8 and write ic acid. If your ion ends in 8, remove the 8 and write us acid. Now, if you end up with these stems when you do this, for example, sulfate would be SO4 2-. Getting rid of the 8 would give you sulf. We're going to change these. Just to make them sound better. But otherwise, everything else operates on the just remove the 8 or the 8 and then add the suffix that is correct. So if you end up with sulf or phosp, we just add a few extra letters to make it sound good. So let's do some examples here. What would I call this? So this ion is acetate right here. That ends in 8, so we get rid of 8 and we write ic acid. And that's what it is, acetic acid. What about this one? What is NO2? This is nitrite. We get rid of the ite and put us acid. Nitrous acid. There you go. So naming acids is pretty straightforward if you know the polyatomic ions, or at least have them handy on a chart. Hopefully you remember when I gave those to you. So same deal here. We've got sulfite and phosphate. So sulfite would become sulfurous acid. Phosphate would become phosphoric acid. Using those changes that we said earlier, just to make the words sound better, I guess. I don't know. All right, I'm going to give you a bunch of these to name, and then, of course, you got to go backwards and write the names into formulas. So that last one is not periodic acid. Be careful. You will need the polyatomic ions, so I'm going to give you 5 minutes to do this. Your polyatomic ions list is at the start of Chapter 6 notes. So go grab those and look there if you need them. I'll be back in a bit. All right, one more minute. We'll go over the answers. All right, so here we go. So this is really just, do you know what the polyatomic ions are, and can you find them? So ClO4 minus is chlorate, which becomes, or I'm sorry, it's perchlorate. Perchloric acid. H-bro, the bro is hypobromite, which becomes hypobromous acid. Oh no, I've been foiled. Hold on. Ah! Not what I meant to push. I hate these buttons down at the bottom. They don't trigger with this tablet for some reason. All right. We've got dichromate here, which becomes dichromic acid. Just taking off the ending and sticking on ic acid or us acid, depending on which ending we have. HCN is cyanide. That follows the IDE rules that we said earlier. So this is hydrocyanic acid. And then finally, PO3 is phosphite, which becomes phosphorus acid. All right. Turning the formulas into names isn't so bad if you have the polyatomic ion list with you. Going backwards, though, is a little bit more difficult. So we've got ic acid. That means that this must be, well, we get rid of this. Sulfate. That's this. And I need enough H's to balance that out. So there you go. Nitric acid becomes nitrate, which is that. There you go. Chromic acid becomes chromate. So chromate is that. There you go. Hypochlorous acid becomes hypochlorite, which is that. There you go. Now, this looks like periodic, but it's actually periodic, which becomes periodate, which is that, which would be this. I'm not actually sure if periodate exists. It might be too reactive. I know iodate is a thing because we titrate that. But... All right, that's naming acids. So now you know how to name everything. Everything that we care about. There are other nomenclature schemes. You're going to learn more about nomenclature in 261, where you name all the alkanes and all the alkenes and all the acids, and or all of the carboxylic acids, I should say, and stuff like that. But for now, this is good enough. Oh, excuse me. All right. Let's draw Lewis structures of everything. Okay, so if you took 140 with me, you remember that we spent a little bit of time in Chapter 7 on drawing Lewis structures. I don't actually know if other instructors do Lewis structures. I want to say Samhita does, but I don't know. And then I think there aren't other 140 instructors. Like, it's just me and Samhita. We're the only one that want to teach 140. I like 140. So yeah, I throw Lewis symbols and Lewis structures in there just for this part. I think it's helpful. So this will be a little bit of a review. What we didn't do in 140 was link the idea of the electron configuration to the Lewis structure. Turns out that all the electron configuration stuff that we did in Chapter 3 is exactly the reason why we get to the octet. So if you've heard of the octet rule and you're wondering where 8 comes from, like, why is 8 important? And the reason that it's important is because... That's not what I meant to write. Thinking ahead here, sorry. I am the worst at writing today. I can't even blame lack of sleep. I slept great last night. There we go. So these blanks are just going to be whatever n you want them to be. So for example, if I pick 3. So if I wrote the electron configuration of something as 3s2, 3p6, how many electrons is that? Dun dun. So you've heard of the octet rule possibly before. Really, the goal here is just to fill the S and P subshells. If you can do that, you end up with a stable ion. And so what Jan Lewis tried to do is he was aware of this fact, but he wanted to create like a system that you could use for like bookkeeping or note-taking or something like that. And what is shown is actually an excerpt from his notes in the laboratory. And so what he tried to do is he tried to orient the 8 electrons around the vertexes of a cube. Vertices, I guess that would be, right? All the corners, basically. And he thought, well, if I can get an electron in every position of each corner of the cube, then it'll be stable. And you can see that he's trying to figure this out with like things like sodium and magnesium. With sodium, he wrote +1 or -7. He wrote a bunch of minuses there. Magnesium could be +2 or -6. Chlorine could be +7 or -1. And then, if I wanted to make an ionic compound, you just put those two things together and try and get 8 somehow. So here's the part where it's chlorine. And then this is the sodium one. We're going to do something pretty similar, except we're not going to use cubes or stuff like that. We're going to draw a Lewis symbol in a different manner. Sorry, my throat got really scratchy there. I had to cough. All right, so the Lewis symbol is actually going to look something like this. So instead of drawing like a cube like this for sulfur, what we're gonna end up doing is something that looks like that. And you've probably seen these before. The Lewis symbol of a element is very simple and straightforward to do. You're going to write the symbol of the element off the periodic table. So if it's like sodium, you write Na. If it's sulfur, you write S. If it's oxygen, you write O, etc. Then what you're going to do is you're going to draw dots around the element 1 dot per valence electron. Remember that a valence electron is any electron that's in the highest n. If you don't know how many there are, write out the electron configuration for your element. And then count all the electrons in the highest n. Those are your valence electrons. You're going to put 1 dot per valence electron. So let's do an example. Here's sodium. I have written the electron configuration for sodium. It's a neon core with 3s1. There's only 1 electron in n equals 3, so there's 1 valence electron. So first step, draw the symbol. Bing. Oh, excuse me, sorry. Second step, draw a dot for each valence electron. There's only 1 valence electron. Boop, there you go. You're all set. This is the easiest thing that you will do in Chem 161. Yay! But it's going to be extremely important, so we want to make sure that we get this idea down pat. I want you to do the same thing for oxygen. I'm going to write the I'm going to let you write the electron configuration. So I want you to draw the valence, write out the electron configuration for oxygen, identify the valence electrons, put dots around your oxygen to get the Lewis symbol. I'll give you 2 minutes to do that while I chug more water. Alright, so here's what we're going to write for oxygen here. Now I've drank enough water, I hope. So there's our electron configuration, 1s2, 2s2, 2p4. We're going to draw the atomic symbol. Boop, there's our oxygen. And we're going to put a dot for each valence electron. Now, there is a little bit of finesse to writing out the electrons because you can think of this as if we were drawing a bunch of orbitals around our oxygen. Now, we're going to assume that they're all the same energy, and if we had 6 electrons to fill in these, we would do something like this, right? We'd put 1 on each orbital, and then we go back and fill in the next ones and pair them as we needed. Now, there's a very specific reason that I'm putting the S in the same energy as the p orbitals here. And we'll get to that in Chapter 5. That's the whole point of Chapter 5. So when I put my dots down, I'm going to treat each of the sides like it's an orbital. And I'm going to go 1 per side, and then I start pairing them. Now, it doesn't matter where your unpaireds and your paireds end up. So if you have something that looks like this is okay. This would be okay. But what would not be okay would be this. This one's no good. And the reason for that is because I have this space right here where an electron could get shoved into, because electrons repel. We're only going to pair them if we have to. Now, not all elements will run into this problem, so if you have less than 4 electrons, you never have to worry about pairing them anyway. Just put them on 1 per side and then 2 per side until you run out. Alright, there you go. I have a bunch of these. I want you to draw their Lewis symbols. What do you think happens with the ions? Well, it changes your valence, or not your valence. It changes your electron configuration, so how would that affect your result? So, I want you to draw these Lewis symbols for all of these elements or ions shown on the screen. I'll give you 5 minutes, then we'll go over the answers. One more minute, we'll go over the answers. All right, so this is going to come down to just writing out the electron configurations for all of these, so I'm going to have to do that. So I got 4 valence electrons, so my carbon is going to have 4 dots around it. Look like that. For lithium, I only need to have 1 valence electron. Now, be careful, it's not this one. That's just a dot that we write for lithium, right? So be mindful of that you don't miscount. Only lithium, well, I guess silicon you had to deal with that, but it's very uncommon that you have to worry about that. All right, I need a periodic table to do these, so I should probably not be just trying to do them from memory. There we go. Where's sulfur? Sulfur is neon 3s2, 3p4. So that means that I would have 6 valence electrons. Something like that. It's good. For chlorine, I have 3s2, 3p5. So chlorine would have 7 valence electrons. So there you go. That looks good. Aluminum is neon 3s2, 3p1. That's 3 valence electrons. There we go. Now, regular old boron would be, we'll just scribble it out. This. But if I make it B+, I get rid of this electron. So B+ would look like this. So I put its valence electrons down. We put a little plus in the corner around some square brackets. So ions tend to go in square brackets when we're drawing their structure or their symbol. Bromine, where's bromine? There it is. So that's argon, 4s2, 3d10, 4p5. Now remember, we only care about the valence layer, highest N. This is where those rules from before, where the textbook was like, the d electrons are the valence electrons. And we're like, nope, they're not. Just, nobody cares. Remember, Wes is watching out for you. All right, I got this here, so I got to increase this by 1. So Br minus would have 8 valence electrons. We do that to it. And then xenon would be krypton 5. Is that 5? Yeah, 5s2. 4d10 that nobody gives a shit about. 5p6. There we go. And so we just do 1, 2, 3, 4, 5, 6, 7, 8. There you go. Looks fantastic to me. All right, so now that we've drawn symbols, we're going to have to draw structures using these symbols. And so the paired electrons and the unpaired electrons are going to become important. Well, that's a problem for future you. Well, future you in 10 minutes. So I apparently closed the timer, so let me get the timer back on screen. And let's get some more Secret of Evermore going. So we'll see you in about 10 minutes. You know, if I could find the track that I want to play. There we go. Alright, we are back. Let me wind this down here. So, we've now drawn the Lewis structures for elements on their own. What we're going to do now is we're going to take the next step, which is what we saw in G.N. Lewis's journal, and that is to try and combine compounds to figure out what electron configurations they achieve in order to learn something about how compounds form. So, the first thing that we want to know is, well, okay, if I combine sodium plus and Cl minus, those form into an ionic compound. That's pretty straightforward. We know how that works. However, what if we take regular elemental sodium and chlorine? So first we're going to play a video. We're going to go back to Lonnie's lab here. We've seen Lonnie's lab several times before, and for some reason... Oh, it is this video. Okay. It's like, why is it not finding my window? It did. All right, so we don't need sound from Lonnie here, but we'll make him real big because this is the face that you will see when you go to sleep at night from now on, I guess. I don't know. And what Lonnie's going to do is he's going to take gaseous chlorine, which you could see in the cylinder here. It's kind of yellow. And he's going to take solid sodium metal, which is down here, stored under mineral oil. He's going to rinse that out with hexane. So first he's doing some setup. He's going to remove the valve from the hose now that the cylinder is charged with chlorine gas, and then set that container aside so that it won't get knocked over or something bad to it. We don't want to fill the room with chlorine gas. That would be bad. Then he's going to cut up a chunk of sodium. The sodium can't have all this oil on it because that's going to just burn away and give us... You know, I don't know why he has to wash it, to be honest. Maybe the mineral oil is too thick and it would take too long to get to the sodium. I don't know. He's rinsing it in hexane. That's not water, that's hexane. Oil is soluble in hexane, but not soluble in water. And we can't rinse the sodium in water anyway. Alright, so now we're going to heat this. The sodium is now in this ladle. If you remember for 140, when you burn sodium, you get like an orangey color. Looks kind of like this. Well, kind of like this. There we go. So now that our sodium is burning with a bright orange flame, we're going to drop it into the chlorine gas, and it will ignite in the presence of chlorine gas. And it will form gaseous sodium chloride. Now, something is happening here at the chemical level in order to make this reaction occur and to make table salt. Now, all of that brown kind of gas that's in there, that will eventually coalesce together into our ionic compound. I don't actually know why it's brown, to be honest. It could just be unreacted chlorine. You could see that when the ladle came out, the ladle is still red, because it was red hot. So this is a very hot reaction. And then this will condense down. You could kind of see down here at the bottom our white solid precipitating, and it actually looks like this on this watch glass. So Lonnie prepared a sample of this earlier for his demonstration, and that you can actually eat this. I would not recommend eating in the laboratory, but, you know, this is why Lonnie has a PhD. He's allowed to eat in whatever lab he wants to. There you go. So, we've seen that we can make ionic compounds with a very energetic explosion type of reaction. Like, it was sparking and hissing, and it was spitting gases out, and those gases got sucked down the fume hood. So, it's a very vigorous, energetic reaction. Why don't we see that sort of thing going on? And the answer to that question is, well, this happened long, long, long ago during the formation of the Earth. These electrons had long since been transferred from metal to nonmetal. Let's examine what happens at the microscopic level. So here is the formula that we just did. I take a sodium atom and a chlorine atom and I introduce them to each other. And what I'm trying to do is I'm trying to get to a full S&P subshell for both elements. And the way that I do this is, well, I just simply move this electron over. Sodium only has one valence electron. It doesn't want it. Chlorine has 7 valence electrons. It would like one more. That would fill chlorine's valence shell. And at the same time, sodium would then have a full n equals 2 valence shell for S and P. So if I do this, now my Lewis structures look like this. And then those two ions are attracted to each other to make an ionic bond because they have opposite charges. And so those opposite charges hold the ions together. Oh, excuse me there. So what I want you to do is, based on what you remember from Chapter 3 / Chem 140 / whatever, you should know what ionic compounds would form if I were to mix ions of these things together. But you can also justify it now using a Lewis structure. So what I want you to do, draw the Lewis symbols for each of the elements. So draw the Lewis symbol for K, draw the Lewis symbol for Br based on their electron configurations. And then I want you to shove electrons around from one element to the other such that everything has a full S and P subshell. Remember, the magic number you're looking for is 8 valence electrons. That'd be S2P6. I'll give you 5 minutes, and we'll go over the answers in a bit. Let's do 2 more minutes and we'll go over the answers. All right, hopefully everybody's finished. We're going to go over here. I got to click on the button over here to do that. All right, so when I draw my Lewis structure, that's going to look like this. So, oops. So if I've got my potassium ends in S1, so it's going to have 1 valence electron. Bromine ends in S2P5, so it has 7 valence electrons. In order to fulfill my octet, I would have to move 1 electron over here like so, and that would mean I have K plus and Br minus. And that'd look like that. And then the ionic compound I would form would be KBr. All right, we do the same thing with calcium and oxygen here. Calcium has 2 valence electrons, oxygen is 6. We get those from the electron configuration. There you go. So that means that we put calcium with 2 plus and oxygen with 2 minus, which has 8 valence electrons around it. There's our ion. Oh, I might have to replace the tip on my my stylus here. Oh, excuse me. I don't know why I apologize for coughing when you guys can't hear me cough. Or, I mean, I guess it's in case, like, maybe you heard me coughing in the mic. Like, I didn't clip the mic fast enough or something. I don't know. All right, so here's our magnesium and chlorine here. So I could do this. And that ion is good. But I still have this. I got to do... Oops. I got to do something with this ion, right? So in the event that you don't have another place on the first atom to put your electron, you could always go find another atom. There's always going to be more chlorine out there, right? So there we go. So now this will have removed its valence electrons. This will have filled its valence electrons. I'm going to omit drawing in the dots here because we're just going to use up all of our time drawing dots everywhere. But that's how we get our ionic compound there. All right, and then we got the next one. Sodium and nitrogen. Oops, I didn't change colors here. There we go. So first I'll get rid of this electron and pass it to nitrogen. We'll put it right there to pair these two. But I'm going to need additional sodiums to do that so that I can get sodium, or not sodium, I'm sorry, nitrogen, its octet. There we go. So now this has 8. These each have gotten rid of their valence electrons. We've got sodium. That's for our Batman fans out there, I guess. I don't know. There's our ionic compound. And similarly, we can do this with aluminum and oxygen here. It just takes a second to get us there. So here's aluminum. There's our oxygen. So I can do this, but then I don't have enough space to put an electron from the aluminum on anything. So we'll get another oxygen here. And then I can do this. But now this oxygen down here needs one more electron, so we got to get another aluminum. And we just have to basically go back and forth until everything is taken care of. So now this one's good, but aluminum's not. And eventually everything will balance out. And there we go. This is good. When I combine all these together, if I add all the positive charges, they add up to all the negative charges, which is what we want. An ionic compound should have a total charge of 0. There's our formula. So we can make ionic compounds by using this Lewis symbol method, which is why, skipping over in Chapter 3, I was like, whatever, it's fine. We could do it here. All right. And you should know what ions are popular for a given element because you want to attain a full S and P subshell, also known as the octet rule, which I believe on the next slide we're actually going to use the words octet rule. Are we? When do I actually say octet rule? It's in like 2 slides. Okay, so it's coming up. All right. On the screen above here, I have 2 fluorine atoms, and I want to ask you the question, how the heck do I move electrons from one to the other in order to make an ionic bond where everybody has a full S and P subshell? And before you think too hard on this, the answer is you can't. Because moving one electron from one fluorine to another... So if I did this, I would only have 6 valence electrons over here. And this one would have 8. This is obviously no good. I'm further away from getting my full S and P subshell, while this one is fine. They're both the same atom, so there's no reason one would do that over the other. The electron density should just be right in the middle the entire time. So how do I get to a full S and P subshell? And the answer is, we cheat. If I just slide those two atoms together and then I go, oh, look at that. Full S&P subshell. Oh, look at that. Full S&P subshell. And what do you notice right here? In the middle where the orbitals overlap, I just put both electrons in both orbitals at the same time. I mean, atoms don't know that. They don't know that the electrons don't belong exclusively to them. Like, each fluorine will have an orbital in between those two fluorine atoms. I'm just putting one pair of electrons in there to occupy both orbitals. And that hooks the molecule together. We're going to talk more about what the shapes of orbitals look like and how this can happen in Chapter 5. Now, obviously, these electrons haven't been transferred. They're shared equally between the two atoms. We also talked about how electrons don't have to be shared totally equally. But the overlap of orbitals still exists. And that's where our electrons live. When we share two electrons, it's clearer to visually see if we represent these as lines rather than dots, because you could cram a lot of dots in there and then you have to count them. Whereas putting a single line in there is very clear and distinct. Putting multiple lines in there is not difficult to discern. But each time we have a bond, we're going to count that as two shared electrons. So the number of electrons around each of these fluorine atoms would be considered to be 8. And if we were looking at their orbitals, we would say, oh, okay, their s orbitals and their p orbitals are full. We're going to be able to do multiple bonds in just a second. But this all brings us to the fact that we keep hitting on 8. 8 is the important number here. And again, that is because for whatever n we put into this blank here, eight is the magic number. If you can fill the s and the p subshell for your valence layer, you will have 8 valence electrons. So this is called the octet rule. The octet rule applies to elements in groups 1 and 2 and 13 through 18. And the reason that it applies to these elements is because these elements don't have d electrons that they have to deal with. Looking at transition metals, the electrons that you get added in are going into the d orbitals. But if we're looking at elements in these groups, 1, 2, or 13 through 18, adding electrons goes into either the s orbitals or the p orbitals. And so they follow this rule. Elements that have d electrons in them follow their own sort of rules. So there is an 18 electron rule for elements in the transition metals that we'll talk about in like 361. I mean, I say we, but what I really mean is you will talk about it. If you go to UW and take Chem, I don't remember what number it is, 351 or something like that. Which I'd really recommend because it's a fantastic class. As a graduate student, I took it. I was required. It was my favorite class. Unfortunately, Jim Mayer is not at UW anymore, so you don't get to do that. Also, unfortunately, none of you are probably chemists, so you'll never have to do that. Ugh. If only biology didn't pay as well. I get why you want to be in biology. Biology is... There's a lot you can do with biology, but chemistry is so cool! You can't see me, but I'm shaking my fist! Alright, so what I want you to do, I want you to play around with just simple Lewis structures here, and try and draw the structures for CF4 and H2O. Now, the way that you're going to do that is, remember, you want to give everything an octet, right? So, how would I make a bond between these two things? Well, if I share these electrons together, I would then make something that looks like that. And then these are waiting for something to happen, which I would then replace this as a line. Oh, if you're doing chemical engineering, you might end up taking a 300 level chem class. I think at that point you end up spending more of your time in engineering, though. Which is also interesting, but it's very physicsy. I'm going to coin that word, physicsy. It's the word physics with the letter Y at the end. Anyway, I want you to draw these two Lewis structures, so CF4 and H2O. I've sort of started CF4 for you. If only I wasn't about to erase everything, right? So, all right, go ahead and try that. We'll go over the answer in just a bit. All right, we'll do 1 or 2 more minutes, and we'll go over the answer. Alright, so hopefully you drew something along the lines of this. Where here's my carbon, and I could take 4 fluorines here. And for my crude Lewis structure, I would do something like this, where I'm pairing the electrons that are unpaired together. And then when I tidy up, because this isn't really a Lewis structure, right? Bonds are attracted through electrical forces. Positive attracts to negative, and all that goes in straight lines. So I need to make all my bonds be straight lines. And so that would look like this. So we can tidy up, and our atom would look like this. And yes, you do have to write in all the electrons, as annoying as it is. There we go. So that would be the Lewis structure for CF4, where I have a central C, and each fluorine is pointed out from it, connecting to one of its unpaired valence electrons. Water, on the other hand, I don't really need to do as much space for, because oxygen looks like this. Each hydrogen only has 1 electron, and so I could just do that. And so there's what my water looks like. Now, if you did it in a straight line where you have the paired electrons on the top and the bottom of oxygen, and the hydrogens come off to the left or the right, totally fine. The orientation in space does not matter. In fact, in a later chapter, what we're going to do is we're going to bust out the molecular model viewer, and I'm going to spin molecules around, and you can see, like, oh, based on your perspective, this looks the same as this, and the paper interpretation on 2D, or the screen interpretation we have here. It's all meant to be a model, and part of the goal of this part of the course is to develop some skill in trying to manipulate molecules on the paper and then visualizing them in your head. So, like, can you take the drawings that I just drew and then, like, spin them around and flip them over? And as you get better at chemistry and spatial awareness, you can totally do that. So, there's my structures that I used a program to draw. It's called Chem Draw. But if you want a program online that lets you draw things, let me type in the link here. So let me get MolView here. And I'm going to just paste this in the chat here. Now, MolView is not intended to be a molecular builder, but you can totally use it as one. And so if you click that, you can then draw your molecules however you want to. It does use organic nomenclature, which does a weird thing with carbons. And we'll talk a little bit about that later. But I don't know. If you're interested in that sort of thing, you play around with it. So now, for hydrogen, you probably noticed that, like, wait a second. I don't have an octet around hydrogen. In fact, I only have 2. Hydrogen follows what's called the duet rule. Hydrogen is really small, and to fill its n equals 1 layer, you just need 2. Filling an S and P subshell for hydrogen is impossible. You can't stick 10 electrons around 1 proton. That proton would be like, help, I can't hold on to this many electrons. But it can deal with 2. 2 is fine. So hydrogen follows the duet rule, which we call an exception to the octet rule. All right, let's make multiple bonds. What would I do with oxygen here? If I want to make everything that is unpaired pair together, I could connect these 2. And then I could connect these 2. And then if I do this, it's a frog. It's not really a frog. It looks really stupid, actually. It looks better when I do this example in class. But if I connect my unpaireds together, I can make 2 bonds. There's no rule that says they can't go on the same atom. So when I tidy up, it'll look like that. And then remember that each pair of electrons can be drawn as a line, and so we're going to draw it like that. So double bonds are just 2 pairs of 2 electrons, or 4 electrons, shared between 2 atoms. You could do this for nitrogen, In fact, I want you to. So I'm going to draw nitrogen here. I'm going to draw another nitrogen here. And I want you to play around with this for exactly 60 seconds and try and find the triple bond. And then I want you to do the same thing with carbon here for exactly 60 seconds and tell me your findings. So we'll check back in about a minute and a half because I've already taken up 30 of your seconds. What are you doing? Go, 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 go. All right, so let's look at nitrogen. Nitrogen's pretty straightforward. We're just going to do this, right? Because those bonds are in straight lines, this more or less works out. So there's what N3 or N2 looks like. It is a triple bond. Now, what about carbon? Could carbon do this? Well, I can do these three, no problem. But what about this one? Can I do this? And it turns out the answer is no, bonds go in straight lines. And if I was going to go in a straight line, I'd bonk into the nucleus, right? So I cannot do a fourth bond here. 4 bonds is not allowed. Oops. I erased my carbon there, but we'll just redraw it. For the purposes of this class, the maximum number of bonds you can have between any two atoms is 3. And that is for geometry constraints. This other bond has to go in these other directions, because that's just where the electron is. It's on the other side of the atom. So I could bond like an H to each of those sides, or another carbon, and then do whatever I want to on that side. But I cannot go above 3 bonds between an atom due to geometric concerns. Now, later on, if you take Chem 300, like I was saying before, you get into all sorts of interesting stuff. And Chem 400, you can actually get more than 3 bonds. You can make a quadruple bond, you can make 5 bonds between an atom. But the atoms that end up doing that, guess what? Transition metals. Yeah, chemistry gets really weird. And if you want to find out more, you have to basically take the degree that I did. I didn't know that when I was signing up for it, but like, yeah, look at the 7 bonds to this metal atom. Like, what? No, don't be ridiculous, but totally does. All right. So the last thing that we're going to talk about today is this method that we've been using to just play connect the dots. Like, it's fun, and it's it works. However, when you get more complicated molecules, it becomes real obnoxious. So if you tried to draw the Lewis structure for, say, benzene, and I give you a bunch of carbons here, and I say, so here's all my carbons, and then I have my hydrogens here. And I say, here you go, connect the dots. And you're going to just, this is what's going to happen. You're going to be like, huh? What do I do? And it's going to be a nightmare. It's going to be terrible real quick, right? So drawing large molecules with this connect the dots method, it's not great. So we need a better method. And so what we're going to do is we're going to use this 5-step plan here to draw the Lewis structure for anything. And we're going to do more of this on Tuesday because we're not going to be able to get through more than just my one example here. But you can go into the weekend looking at the homework practice and trying to draw a few of these Lewis structures. So here's our 5-step plan. So step 1, I'm going to give you a molecule. And for our demo, the molecule I'm going to give you is CO2. You could totally do CO2 using connect the dots. But we're going to use this approach because this will work for anything. So first step, count all the valence electrons. Now, how many valence electrons does something have? Well, we know carbon has this for its electron configuration, right? So we would say carbon has 4 valence electrons. That's how many dots we've been drawing around it. So each time I hit a carbon, I would add that to my bank. I could do the same thing for oxygen. There's my valence layer. So each oxygen is 6 valence electrons. But this is going to get super tedious writing out electron configurations over and over and over and over and over again. So how about we just never write an electron configuration again? That sounds great, right? Now, I wouldn't want to deny you guys the writing of electron configurations because we literally spent 4 weeks doing this. But, you know, I don't know. We've been here for what? Almost 8 full weeks now at this point? I think I could trust you with a little secret. If we go over to p-table, which I'm going to link over here, and we'll put this on the screen. And this is what a student was talking about earlier. Like, can't we just do this? Well, yeah, you totally can. So here's my periodic table. I guess we'll put these guys on there too, but not really important here. If you look at the group number that these elements are in, the ones digit tells you how many valence electrons you have. So everything in the first column would have 1 electron. Actually, can I put the electrons? Yeah, I could just do this. There we go. I don't know what that did to the capture, though. There we go. Okay. So this is my S block over here. So everything, this is 1s1, 1s2. This helium should actually be over here, but it's been moved over here to fit in the S block. For the P blocks, those are over here. So, for example, lithium, I'd go 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, etc. But what you'll notice is that for oxygen, which has 6 valence electrons, it's in group 16. So when you go to the periodic table, just take the ones digit of the group number, and that's how many valence electrons that element has for anything that's in the S or the P block. Those are the groups that we care about. Ignore D, ignore F. We're never going to do anything with those two, but these two right here. Woo, strobe. So that's going to make our counting valence electrons a lot easier, because now we don't have to deal with electron configurations again. So, for instance, this carbon gives you 4. There are 2 oxygens, each gives you 6. 6 times 2 is 12, plus 4 is 16. So when I draw the Lewis structure of CO2, I've got to have 16 electrons. Step number 2 is going to be to draw the framework of your molecule based on what the formula tells you. The central atom is listed first, unless the central atom is H. H cannot be a central atom. In our structure, the less electronegative an atom is, the more likely it is going to be the central atom. So if I have my CO2 here with my 16 electrons, I would put carbon in the middle, and I put the oxygens around it. And I'm just going to bond them together. So bond, bond. Bonds have pairs of electrons in them. So this is 2 electrons. And so is this. So I need to pay for those electrons. They come out of the valence bank. So that was step 2. Step 3 is going to be using the electrons that you have in your bank, put them around the outer atoms, and give them octets. Always do the outer atoms first, otherwise you get the wrong answer when you finish your structure. So we go back over here. That's going to look like this. I have 12 electrons left, so let's give octets to outer atoms first. So 2, 4, 6. There's my octet. So now I have 6 electrons left. 2, 4, 6. There's my octet. Now I have no electrons left, so I've used all my electrons. Do I have an octet around these atoms? I do, because I have pair, pair, pair. That's 6, and then a bond counts as 2, so that's 8. The fourth step is to place all remaining electrons on the central atom. Now, we don't have any extra electrons, so we're going to ignore that step. But we'll come back to that on Tuesday. Step 5, if you did not make an octet for your central atom because you ran out of electrons, start sharing electrons to form multiple bonds. So you can see this in practice here. My carbon only has 4 electrons. It's got the 2 bonds. How do I get more electrons? Well, what I'm going to do is I'm going to take a pair of electrons. I'm going to make a bond out of this. So I'm going to erase this. And do this. And I'm going to do the same thing over here. We're going to erase this guy. And do that. So now everything has an octet. Because I've got electron, electron, pair, pair, electron, electron. So that's 8. Electron, 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 pair, pair. So that's 8. And then 2, 4, 6, 8 for the electrons around carbon. They're all tied up in bonds, but everything has an octet. So there's our structure. All right, that's all the time we have, unfortunately, for today. But you can see that by using this 5-step approach, we can draw the Lewis structure for CO2, and we're actually going to do this for anything. So when we come back on Tuesday, we're going to pick up here. I'm going to do ammonia, and I'm going to have you try this for any structure that I give you. And that's that. So I'm going to go and get that video online for the lab worksheet number 4. Please make sure that you check that out because it's not difficult, but it is cumbersome if you have not worked in Excel before. With things like a formula command, like typing equals, and then a formula referring to cells, referring to a fixed cell, that sort of thing. So we'll get that going. And then quiz number 3 for chapter 3. Just let's finish it off. Let's get all the chapter 3 stuff done. Due tonight, closes tomorrow. Thanks for watching. Have a wonderful rest of your weekend. Go out and enjoy the sun. It's supposed to be like 70 this weekend. It's about time, isn't it? Enjoy spring.